Hello again and welcome back. For this video, we're going to talk about simplifying radical expressions, and this is going to be part 1. Our goals are for part 1, simplify square roots, and for part 2, we're going to do simplifying of cube roots. We have a few vocabulary here, and these are going to be defined on the next page. All right, for the first one here, we have radical expression. It's an expression that contains a radical, such as a square root, and the radical sign looks like this. And the bar that goes above it, well, the bar that goes above it is simply like a grouping symbol. So anything that's under that bar is part of the square root. Anything that's outside the bar is not. What is a square root? Okay, so a square root of a number x is another number y if y to the second power is equal to x itself. So in other words, square root of 36 is 6, and the reason for that is when you take 6 and you raise it to the second power, in other words, you're timesing it by itself, you get 36. A perfect square, any rational number with a square root that is also a rational number. 16 and 2.25 are perfect squares because they are rational numbers and they have rational square roots of 4 and 1.5. And a rational number is any number that can be expressed as the ratio of a over b, where a and b are both integers. So it's the ratio of two integers. That's what a rational number is. Cube root is similar to a square root, except the cube root of a number x is a number y if y raised to the third power instead of the second power, it's raised to the third power is equal to x. So an example there, the cube root of 27 is 3 because 3 when raised to the third power gives you the 27. So the cube root of that goes back to 3. First rule here is the product property of squares. So any non-negative real numbers a and b, the square root of a times b is the same thing as the square root of a times the square root of b. So right here we have the square root of a times b. That means we can break that out into the square root of a times the square root of b and then multiply them afterwards. The little special caveat here we have is a and b have to be greater than 0, meaning they have to be positive. We don't want negatives under the radical sign. We'll talk about that another time. An example here, and I think the example here was supposed to be the square root of 4 times 16. And the square root of 4 times 16 can be rewritten as the square root of 4, square root of 16 with a times between them. And then you can take the square root of each one individually. So we got square root of 4 is 2, and the square root of 16 is 4, and then multiply the answers to get 8. We also have a quotient property, which is the same thing as the product property, only with division. So for any real numbers a and b, again, we want a and b to be non-negatives. The square root of a divided by b is equal to the square root of a and the square root of b then divided. So over here we have square root of this fraction a over b. And that's the same thing as taking the square root of the numerator and the square root of the denominator separately and then dividing them. So looking at this example here, we can actually simplify the 100 over 4 and get 25, and the square root of 25 is 5. But we use that example then to show that you can actually take the square root of the numerator, which is 100 first, square root of the denominator, which is 4 second, so we get a 10 and a 2, and then divide afterwards, and we still get the same 5 we had over here. Okay, so here are some rules for simplifying radicals or simplifying square roots. So a square root is in simplest form if these 3 conditions are true. So all 3 conditions have to be true. The square root contains no perfect square factors other than 1. Remember, factors are numbers to be multiplied. So an example here, if I have the square root of 5, the factors of that are just 5 and 1. And even though 1 is a perfect square factor, there's nothing you can do with it. But 5 is not a perfect square, so square root of 5 is simplified. If I had the square root of 8 on there, the square root of 8 can be rewritten as the square root of 4 times the square root of 2. And it turns out that 4 is not a perfect square, so we have to simplify that further, which means the square root of 8 is not simplified. The second rule is the square root cannot contain any fractions in it. So let's say I have the fraction 16 over 25, and I put that whole thing under a radical. Well, that is not allowed, so that quotient rule is where we use here. So we have the square root of 16 divided by square root of 25. So I no longer have a fraction under the radical. But that produces another problem for rule number 3. You can't have any square roots in the denominator of a fraction. Well, this one that I have up here self-corrects because the square root of 25 is 5, so there's no more radicals there. And the numerator, of course, the square root of 16 is 4, so this would be completely simplified. There's no more radicals. Now, even if I had a radical in the numerator, but no radical in the denominator, such as this is still simplified because there's no perfect squares other than 1 and 3, and there's no radicals in the denominator, and the fraction itself is not under a radical, so all three conditions are met. So to start simplifying square roots, now the easiest way to simplify a square root is to know what the largest perfect square factor is within the number. The problem is not everybody knows what the largest perfect square factor is. So the way we're going to solve this one is to use a factor tree. We're going to write the prime factorization of 72 and then show you how to simplify it. So the first thing I'm going to do is rewrite this as 8 times 9. Remember, this whole thing is under the radicals, but I'll add the radicals at the end. Neither of these are prime numbers, so I'm going to break it down again to 4 times 2. That's a prime, so I'm going to put a double underline there. And 9 is 3 times 3, and those are both primes. And then the 4, though, can be broken down further into 2 times 2, so I got a prime and a prime. So the prime factorization of 72 is 2 times 2 times 2 times 3 times 3. If you remember, square roots will undo second power. So the square root of 4 squared is just going to give us 4. So every group of 2 is a perfect square. And a perfect square is something that's been raised to the second power. So as you can see, I have a group of 2 here, which is 2 squared. Bring down my other 2. I have a group of 2 3s here, which is 3 squared. So this first number and this last number are actually perfect squares. So if I write them under radicals, so I'm going to write that up at the top, the square root of 2 squared times the square root of 2. Remember, all these numbers were under the radical, so I got to put them back under there. And the square root of 3 to the second. The first one right here, the square root of 2 squared is just 2, because 2 squared is 4, and the square root of that is 2. The square root of 2 to the first cannot be simplified, so I'm going to leave it under the radical. Bring my times down. And my square root of 3 squared is going to be just 3, because 3 to the second power is 9, and the square root of 9 is 3. Then I'm going to reorder these into 2 times 3 times the square root of 2, and then simplify a little bit further. 2 times 3 is going to give me 6 times the square root of 2. So 6 square root of 2 is the simplified version of the square root of 72. Now, as I said earlier, the quickest way to do this is to find the largest perfect square factor of 72. So the shortcut there would be to recognize that the square root of 72 is actually equal to the square root of 36 times the square root of 2. And 36 is a perfect square, so the square root of 36 is 6 square root of 2, and you can see we get the same answer that we had over here. Now we want to do multiplying of square roots. So the first thing you might want to do is to multiply these two numbers together, and you end up with the square root of 240. Now there are shortcuts a way around this, but I'm going to go the long way for now. And now I got to find the largest perfect square factor of 240. Now maybe we don't know what it is, so instead what we're going to do is create a factor tree out of 240 and rewrite it as prime numbers only. So the two factors that come to mind would be 10 times 24. Neither of those are prime numbers, so I got to keep going. I got 5 times 2. Both of those are prime, so I'm going to double underline them. Then I've got 3 times 8, and that's a prime. 8 can be broken into 4 times 2, and that's a prime. And 4 can be broken into 2 times 2, and that's prime also. So if I list all the prime numbers from smallest to biggest, I list them in order. So I've got 1, 2, 3, I got 4 2s, so 2 times 2 times 2 times 2. Then I've got a 3 times 3 times, and then I've got the 5. Now remember, a perfect square is created every time you multiply a number by itself. So there's a group of 2, which is 2 squared. Here's another group of 2, which is 2 squared. The 3 and the 5 don't have any groups to go with, so 3 to the first times 5 to the first. Now if I put all these under radicals, because that's what they were, that make 240, they're all under radicals. And now we need to simplify each of the radicals, so 2 squared, and then I take the square root of that. This one becomes just a 2. Bring down my times, and the square root of 2 squared, this one just becomes a 2. And the square root of 3, I cannot do anything with it. It's not simplifiable. And the same thing with the square root of 5. And now all I got to do is multiply these together. So I got 2 times 2, which is going to be 4. And then these are irrationals, and I can multiply those together, and that will give me the square root of 15. So back up here at the top, I have 4 square root of 15. Now the shortcut to this would have been to realize that 240 can be rewritten as the square root of 16 times the square root of 15, but not many people know that the square root is, that 16 is a perfect square factor of 240. And if I take the square root of 16, you can see we get 4 and square root of 15 again, which is the same answer that we got up here. Now they want us to divide square roots. Now what I would do first is see the 24 and the 27. Is there any factors I can reduce them by? I want to reduce everything in that fraction first, because right now you can't have a fraction under the radical sign. That violates the second rule there. So I see they have a greatest common factor of 3. So when I divide the first one here by 3, I end up with an 8. And when I divide the bottom one by 3, I end up with a 9. And again, these are both under the radical. Now we use the quotient rules of radicals, or the division rules of radicals, which means I can separate this into the square root of 8 over the square root of 9, put my equal sign, and the bottom one is easy because the square root of 9 is just 3. 9 is a perfect square. There's no need to rewrite this as 3 squared, bringing the 3 out. I happen to know this is just 3, so I can just simplify that to 3. The 8, however, I should probably rewrite that as 4 times 2, and there's a prime number. And 4 would make 2 times 2, and those are both primes. So I got 2 times 2 times 2 to make 8, but remember I'm looking for groups of 2 which are perfect squares, so that makes 2 to the second times 2. These are both under the radical, but square root of 2 squared is just 2, and the square root of 2 just attaches to it because it's not a perfect square. It has no other pairing. So I write the top as 2 square root of 2 over 3, and this is the simplified form. Okay, now they want us to simplify square roots with variables in it. And I'm going to do each of these parts individually and then bring them back together. The first part should be pretty easy because we've been doing it. So I'm going to take the 525 and make a factor tree down to prime factors. So it looks like a 25 might go into there. And it turns out that that's 25 times 21. If the 5 is all you know, you can use the 5. The 25 is not a perfect, or not a prime number, so I got to keep dividing that out to 5 times 5. Those are primes. And then 21 is 3 times 7, and those are both prime numbers. So this can be written as 5 squared times 3 times 7. Remember, all of these are under radicals. So this simplifies into 5 times the square root of 21. Remember, up here, the radical undoes the power of 2, so 5 squared of 21. And I'm going to times that with what I get from the next number. Now, something we haven't talked about yet is variables with exponents. So I'm going to do an example over here. So if I have, let's say, b to the 6th power. Well, b to the 6th power, the square root of that, b to the 6th can be rewritten as b to the 3rd raised to the 2nd using the power of a power rule. So I can write that backwards. As it turns out, I've got a power of 2 and a square root, and they're going to undo each other, leaving b to the 3rd power coming out. Notice that this power of 3 is half of the 6, which means every even exponent on a variable is a perfect square, and it comes out half as big. So that's the shortcut there. I might want to write that down. Every even exponent is a perfect square, and it comes out of the radical half as big, or the exponent comes out half as big. So the first one I have here is x to the 4th, and again, that's under the radical, and that is a perfect square. So the square root of x to the 4th is x to the 2nd. I'm going to bring that all the way down to the bottom. Now we got a y to the 5th. The problem with the y to the 5th is the 5 is not an even number, so it's not a perfect square. However, I can break y to the 5th into y to the 4th times y to the 1st. So you always go to the next even number down. You can't make your exponents higher, but you can break them into smaller parts. And y to the 4th is the next perfect square below 5, so square root of both. And again, the square root of y to the 4th is going to come out as y to the 2nd, and I still have a y to the 1st left under the radical. And I can do exactly the same thing for the z, so the square root of z to the 5th can be broken into the square root of z to the 4th, that's the next perfect square below 5, times z to the square root of z to the 1st, and z to the 4th, the square root of that is going to give you just z to the 2nd, and we still have a square root of z left over attached to the end. Now when you go to multiply these together, you multiply the numbers outside the radicals together, and you multiply the numbers in the radicals together. So you get 5 times x squared times y squared times z, and that will give us 5x squared y squared z squared. So I took care of all of those. And now I look back at my radicals. I have a square root of 21 times the square root of y times the square root of z, and that will give me the square root of 21yz, and this becomes the fully simplified expression. For our last example here, we're going to write and solve a radical equation. Sarah uses an online calculator to determine how much interest she would accrue in a savings account after 2 years. She plans to invest, I'm going to circle that one, invest $750, and the calculator determines that she could have $780, but that's after 2 years. So this is the starting amount, and this is after 2 years. She can find the interest rate, which is R, by using the formula of R equals the square root of A over P minus 1, where A is the amount after the 2 years, so A is going to be the amount after 2 years. I'm going to write that down. R equals A was, amount after 2 years was 780, divided by P, and P was the initial investment, which was 750, minus 1 from the whole. Now, notice that the minus 1 is not under the bar up here for the radical, so that's not part of the radical, just the fraction 780 over 750. So I'm going to use a calculator on this one. So R is going to equal the square root of, now 780 divided by 750 gives me 1.04. And now I got to do the square root of 1.04. That's going to give me approximately 1.0198 and minus 1 at the end of that. So R, the rate, is going to equal, now 1.0198 minus 1 is going to give me 0.0198. And this is actually the decimal equivalency of the interest rate. So if we want to turn it to a percent, you just times it by 100, and you can see we end up with 1.98% as the interest rate.